decibel like gain or loss, but I don't fully understand, like, how would you relate that to like when you're talking about like gain on or is that?
Well-
Kind of jumping again.
A little, but it's okay. Antenna gain technically isn't gain because there's no power gain. If you put 100 watts into the antenna, it's still 100 watts into the antenna.
Right.
If it's say a vertical antenna, it's pretty much omnidirectional. So you have a radiation pattern that's like a big toroid. So the radiation density is basically the same in any direction. So it really has almost no gain. The way they measure some is because above it, there's no radiation. So when you compare the broadside to along the length of it, there is a gain ratio, higher radiation density.
Okay.
So that's why you see a little bit of gain on something like a vertical antenna. When you have a beam antenna, like a Yagi, where you're using directors and reflectors to shape the beam. So it's like a flashlight, beams pointing this way. You still only have that 100 watts, but now it's all concentrated in one direction.
Yeah.
So when you compare the radiation density in that direction to, say, the side or the rear, that's where you see the gain.
Okay, so.
But it's not, in that case, it's not really a power gain.
Right. So a more like focused directional antenna with
Right.
higher gain. because
Right,
there's a
directional gain.
difference in the ratio. Okay.
Right.
So you.
Now, in an amplifier, you'll have power gain.
Right.
So if you have 10 watts in and 100 watts out,
Yeah.
okay, then you've got a dB gain of 10 for that amplifier.
Appreciate it. Yeah, we would refer to a different antenna high gain, and I had to jump. I understand we really understood what the dB was used for.
Okay, let's see. Oh, components.
Got someone trying to get in there.
Oh. Oh, Mr. Hunter. Hello there.
Good morning.
Good morning. Are you
I'm
still
late
in,
again.
you still in New Mexico?
I'm still in New Mexico here. We're still in school session until Wednesday. And so we're still wrapping up the year here. We have our middle school graduation here on Tuesday.
Okay.
Yeah, so then Wednesday will be the last day, thankfully. Are schools out in your area?
I don't know. Oh, I guess so.
Yeah, a lot of schools are out across the country. I think we're the last school to get out for the summer.
Cool.
And we're the first ones to go back to school. It's remarkable how
Okay.
short our summer is.
Well, you're welcome to join us. We're getting close to the end.
Okay, yeah, I'm here finally.
Okay. We're getting ready to talk about components.
Okay.
Okay, so we're going to talk about physical devices that represent resistance, and then talk about new things, capacitors and inductors, batteries, semiconductor devices, diodes and transistors, get into schematic diagrams and some resonant and tuned circuits, and then some other components like relays and optocouplers and things like that. We won't cover all of that in these two sessions. So we know that resistors oppose the flow of current. And we use R to represent them and a value in ohms. Obviously, the higher the resistance, the lower the current for a given voltage. Physically, they tend to come in standard values, where the cheapest ones obviously are only 20% accurate. If it says that it's 1,000 ohm resistor, it means it's 1,000 ohms plus or minus 20%.
Okay.
You can get them down to very high precision, actually less than 1%. The picture on the right shows a sample of typical through-hole resistors. More and more on today's stuff, you're finding surface mount, which was really too small to put on that chart. They're like 1/8 of an inch long or less. They get very, very small. Sometimes we have a variable resistor. We call them potentiometers in a lot of cases. And they're used in the audio world as a volume control, or at least they used to. Anything modern, those rotary controls are normally going to be an encoder, where it's the computer's counting steps as you rotate it and doing the volume control function for you without it actually being a potentiometer anymore. You will see them also on power supplies as the voltage adjustment control. The schematic symbol that's used to represent a resistor is that little squiggly line down there. Typically, it's 3 up and down squiggles. Physically, you don't see many carbon composition anymore. It's used to be the old style resistor, where it was actually some carbon composition material that determined its resistivity. And they would put whatever amount inside that package that was required for the resistance they were trying to make. Though it was very hard to get those at high precision just because of the way they were made. When they went to these carbon or metal film type resistors, where they actually plate a film and then etch it in order to change the length of it and the width of it, they can control the resistance of that film. And they can keep it non-inductive, so it looks like a pure resistance. You'll see these bigger resistors called wire wound, and it's actually made from a winding of like a nichrome or some high resistance wire to create the resistance and handle a lot of power. You only see those used in DC type stuff or low frequency because of the inductance due to the wire. So it acts like an inductor in addition to a resistor. So they're not very useful at any kind of high frequencies. This is just another one of those showing the water analogy for Ohm's law. Well, I might point out, even though it's not a exam thing, you notice the little colored stripes. That's how the values are marked, or at least used to be. What's called the RETMA color code, and each color represented a different number. So that's how you determine the value and the percentage of it. When we talk about potentiometer, that's what a potentiometer typical one looks like. That one happened to be like a PC mount type. And it consists of 3 terminals. You have the 2 N terminals. And it's, say that was say 50,000 ohm potentiometer. It would measure 50,000 ohms between those 2 N terminals. You have that middle terminal, which actually has a little wiper, and that resistance film is in a circle inside. So it moves along that just like it's shown here. And it varies the amount of resistance between the slider and one of the terminals. So that's where you get a variable resistance out of it. So depending on how you're using it, you can use it as a 3-terminal device as a potentiometer, or basically a 2-terminal device as a variable resistor. So what electrical component opposes the flow of current in a DC circuit?
Bravo, resistor.
Bravo. What type of component is often used as an adjustable volume control?
Sweet.
Okay.
What electrical parameters controlled by a potentiometer?
Bravo.
Bravo. Okay. Next component is a capacitor. We haven't talked about these before. It's essentially 2 conductive surfaces that are separated by some form of insulator. We call it a dielectric. And if you remember from that one chart that showed the E field between the 2 plates or 2 conductors, and the closer together they were, the higher the field was. Well, that's the way the capacitor works. You have that electric field, one side will be positively charged and the other negative because it doesn't conduct current. Okay, it just accumulates electrons on one side and positive ions on the other, and creates that, and that potential difference creates the electric field between them. And that's where it actually stores energy. So depending on the separation of the plates and the area of those plates determines the capacitance. And we call that ability to store energy in the electric field as capacitance. Now, a little bit we'll talk about an inductor, which stores energy in a magnetic field. And that's the basic difference. Capacitors use the electric field, inductors use the magnetic field. And radio waves that we'll talk about are electromagnetic waves composed of an electric and a magnetic field that are at right angles to one another or in quadrature. We specify capacitance, or the ability to store energy in that field, in farads. We represent capacitance with a capital C, and we use capital F for microfaraday to represent the capacitance value, and we call those farads. So 1 farad is equal to 1 coulomb per volt. This is a lot of typical capacitors. You see over here some of these surface mount little type tantalums and ceramics. They're really out of scale compared to these other devices. We also have things called electrolytics, we'll talk about in a little bit. Most of these capacitors are either some sort of, like in the case of the ceramics, it's a ceramic dielectric with a metallic coating on each side to form the conductive plates. So that's where it gets the capacitance. In some cases, they'll do multiple layers to get more capacitance. A lot of the older style capacitors, which, well, I guess some of these on here, these tubular ones are actually made by having these conductive plates as foil separated by some sort of thin insulator, and you roll them up, get a lot of surface area in a small package.
The electrolytic capacitors in older electronics have a tendency to blow up. So that's one of the things that you're looking at whenever you try to restore something. Like I've got an old console stereo with the turntable and everything. And before I fire it up, before I restore it, fire it up, I want to replace all those capacitors, because try to put power on them when they're 30 years old, 40 years old, they're probably gonna explode.
Yeah, this top one is showing the flat plate capacitor.
Can I ask a quick question, Rob?
Sure.
Okay, on the last slide, you're showing was it the three prong terminal capacitor?
Yeah.
Yeah, I have a bunch of those. I got them on clearance over at a electronics store. What are those used for, and how do I hook those up?
Well, that's why you have a bunch of them on clearance, because they're not used much. They're kind of special purpose. I don't
Okay.
really know. I'd have to look at a data sheet for it.
Okay. I got like 1,000 of them. I got like 2 boxes of them. For like $5. And now the business is out of business, and I should have asked them what they were used for and how I use them.
They just look neat, so you bought them, right?
Yes. Well, you can't avoid like $10, Oh my gosh, this is the coolest thing ever. Yes, I'll take it.
Okay. One thing I'll point out here on the flat plate, one of the first capacitors was done by Benjamin Franklin, called the Franklin Square. And he actually took a square sheet of glass and put a metal plate on each side of it and made a capacitor out of it. Here's another water analogy where the amount of water in the tank, okay, is the amount of charge that's being stored. And this actual size of the bucket is proportional to the amount of capacitance. So basically, the larger the bucket, the higher the capacitance, the more charge it can store for a given voltage. Here's the actual definition for determining the value of capacitance. You don't need to know that formula. But you can see there where the amount is proportional to the spacing of those plates, because as this spacing, which is D, gets smaller, the capacitance value gets larger. So it's the area of them times the permittivity value, which has to do with the dielectric and other things, and the distance. And that's how you basically calculate the amount of capacitance. This kind of shows how the charges are formed on the plates, where you'll have a positive charge on one side and negative on the other. And that field in there is where the actual energy is stored, depending on the amount of charge and the voltage on those. When we apply, like in this circuit, when we apply a voltage to that capacitor that has no charge on it initially, it's going to charge up in this time fashion because there's a series resistance. And that gives us what the product of these two values gives us a time constant. So it will charge up in 5 time constants to 99% of the input voltage. So in 1 time constant, it will go up to 63.5, I think it is. It's an odd number like that. Approximately 5/8. In 2 time constants, it will do another 5/8 of the difference and exponentially up. So we figured 5 time constants is charged up. The same thing for discharging it. If it's discharging through the same value resistance, it's going to have the same kind of curve. So the time constant value is going to be the same. What type of electrical component consists of conductive surfaces separated by an insulator?
Delta, yep.
Yep. What electrical component stores energy in an electric field? All right.
Bravo.
Just got a question.
No math, huh?
No math.
What describes the
Yet.
ability to store energy in an electric field? So what's the ability?
Delta.
Yeah.
Capacitance.
What's the unit of capacitance?
Hey.
That.
Okay, inductors, different animal. We take a piece of wire and coil it up to increase the inductance. And when current flows through that wire coil, it creates a magnetic field around the wire. And we store energy in that magnetic field as long as current is flowing through the wire. And we call that ability inductance. So it's the ability to store energy in a magnetic field. It's composed of capacitance, which is the ability to store energy in an electric field. The unit of inductance is the Henry with a capital H because it's named after a guy named Henry. And we use the capital L to represent inductance. Where we use C for capacitance, R for resistance, L for inductance. So this just shows the magnetic lines of force as we run a current through there. You're actually getting a circular magnetic field around the wire, but as it's coiled up like that, they tend to add in the center. So you have a concentrated magnetic field going through the center of the coil where it's smaller and spread out outside of it. The water flow analogy for an inductor is this little turbine wheel and a flywheel, because it has effectively, it's equivalent to inertia. So when we first apply some water pressure, it's going to try to turn that turbine, but the flywheel is going to resist. So it's eventually going to start turning and finally get up to speed. When we stop the pressure, it's going to continue to turn for a while until it dissipates that energy. So it's stored, mechanically, it stored energy in the flywheel as angular momentum. Electrically, it's storing energy in the magnetic field, but it acts kind of like the turbine flywheel. And we call when we make that coil, that inductance, we call it self-inductance, because it's induced from that single coil alone. And a little bit later, we'll talk about mutual inductance, where we have two coils that are closely coupled. So we'll have we call that a transformer, and it uses the mutual inductance between the two. The formula for inductance is down here, and you can see that again, how close the coils are together will increase the inductance, as well as the area. So the larger the coil and the closer they are together, the more inductance you're going to have. Which seems a little counterintuitive. You would think that the smaller one would be more, but it's a larger one gives you more inductance. You actually wind up having inductance just on a straight wire, very small, but it makes a difference at high frequencies. Nothing new on that one. There's, when I talked about in the mechanical analogy with the flywheel, where it initially resists, that's the way the inductor works. Okay, it will initially appear at a very high resistance or impedance, and slowly decrease as it charges up. And that's due to Faraday's law, where it has what we call a back EMF, which is equivalent to the amount of inductance and the rate of change of the current. So the faster the current tries to change, the higher the opposing magnetic field is. It's much more important when you get into motors and things, but it's also in transformers.
What does T represent? I'm sorry, on that equation?
The T,
The T,
let's
the
see.
change of T.
Oh, time.
Okay, just want to make sure. Okay,
Right.
gotcha. Time.
It's the
Okay.
delta current per delta time.
Gotcha.
Okay. We take a typical coil like that and put it in series with a resistor like we did the capacitor and apply a voltage. And we're going to see initially, because it appears to be a very high resistance, we're going to see that in this case, I think, yeah, 10 volts. And as it starts storing energy, okay, the voltage drops across it until it appears like it's essentially a short circuit. So when we take the current away at this point, it still has all that energy stored in the magnetic field that starts to collapse. So that's where you get, I talked about the back EMF, which gives you an opposing voltage as it releases its stored energy back into the circuit. So it'll have a discharge pattern like that. Whereas the capacitor ramped up this way, the inductor starts here and goes kind of just the opposite. So what electrical component is typically constructed as a coil of wire?
Delta.
What type of electrical component stores energy in a magnetic field?
Charlie.
C, inductor.
What describes the ability to store energy in a magnetic field?
Capacitance.
You didn't read them all, did you?
D. Delta.
Inductance.
Yeah.
Magnetic field, inductance.
It's similar, it's the question is similar to the capacitance because of the stored energy field and electromagnetic field, right? It's similar.
What is the unit of inductance? Oh, Henry. Henry repeating arms. Okay, batteries, another component. You're familiar with flashlight batteries. Those are carbon zinc. It's a non-rechargeable battery, and it works with a chemical process between the zinc and the carbon and whatever that kind of electrolyte is. And once it runs down, you can't charge. It's a non-reversible chemical process. In the case of more modern batteries like lithium ion, for instance, that is a reversible chemical process. So you can recharge that type of battery. Just like a nickel cadmium or a lead acid, like your car battery, those are all rechargeable batteries. And this is just showing your lead acid, nickel cadmium, lithium ion, nickel metal hydride. You don't see much of those anymore. Are all rechargeable batteries. Your carbon zinc or your alkaline or mercury, watch batteries, for instance, the small ones, none of those are rechargeable. So which of the following battery chemistries is not rechargeable?
B.
Bravo.
Bravo. Which of the following battery chemistries is rechargeable?
Bravo.
Well, you got the. All of them.
D,
All of
D,
them.
delta.
Okay, so we learned many times resistors oppose current flow, potentiometers can be used as volume controls or adjustable resistors. Capacitors store energy in an electric field. Inductors store energy in a magnetic field. And batteries store energy in the electrolyte as a chemical process.